start now. Welcome everybody. It seems that we have picked not quite a very nice day for you all to come to this presentation. I can't control the weather, but we'll try to control everything else so that you have a pleasant time today. I'm Shirley Fenton, manager of the Infonet Project and one of your hosts today. This seminar series is a joint effort between the Waterloo Institute for Health Informatics Research and the Infonet Project. So thank you for joining us as we continue our series of seminars focused on health informatics tools for the future. You may notice as well, we've got a lot of equipment around here. We are continuing our exploration of webcasting, so those of you that are coming in by distance, welcome. Last month was our first time for this series that we did a webcast. It was quite successful. It was a learning experience, but it was quite successful. So we want to continue to webcast these seminars so that our colleagues at a distance can join in with us. We are very thankful to KDMI in Toronto for the e-presence technology that we're using. Ron Becker is leading the charge there in this effort. And of course to our technical team here, Kyle Young and Anthony Robbins. So thanks, guys. We're very pleased to have today Tom Chau. He's the coordinator of Intelligent Systems Research at Bloorview MacMillan Children's Centre, the largest pediatric rehabilitation facility in Ontario. I first learned of Tom and his research one evening as I was channel flipping. I was immediately taken in with the research that he was doing and went about trying to figure out how we could get him here to Waterloo to speak to us. So it is my pleasure now to introduce to you David Johnson, President of the University of Waterloo, and David will introduce our speaker.
Thank you very much, Shirley. What a pleasure it is to be here and to welcome Tom. It's a welcome home to Tom. Shirley has given a partial introduction. You see part of it on the screen. He is a PhD graduate of this university in our systems design department and worked in that famous PAMI lab that Andrew Wong and Mohammed Kamal and others have pioneered and have done so many wonderful inventive things with a remarkable group of students coming through. Tom left that and entered the business world with IBM, where he was one of their great representatives on their enterprise content management projects in the transformation of that organization from not simply an equipment supplier but a service provider. And having done his tour of duty in industry, decided that he would return to research and teaching and found himself back, I think, Tom, at Toronto Sick Children's Hospital. And as I understand it, really had to make your own way, find your own salary, get your own grants, and ultimately create your own research chair. And today, a few short years later, has established a Canada Research Chair in Paediatric Rehabilitation Engineering. And in describing his work, he speaks about a biopsychosocial model. And what strikes you about that, and I think what will strike you among other things about Tom's presentation today, is how transdisciplinary, how integrative, how adaptive, how entrepreneurial is this work. We often say the most interesting problems in a university today, particularly in the 21st century, are those problems which cannot depend on the expertise of a single discipline for their answer, that we are dependent on one another. One of the great intellectual and scientific leaders and great teachers of our country and our history was Wilder Penfield, who founded the Montreal Neurological Institute in Montreal about 1925. When Dr. Penfield wrote his autobiography some 50 years or so later, he entitled it No Man Alone. We'd say no person alone today. Those who knew Dr. Penfield personally would say that's quite striking because he always seemed to be a towering figure, a person alone. But he understood very early that he was very little if he did not learn how to work with others. And what Penfield did that was quite remarkable in the early days of mapping the brain with very crude instruments is he depended on the expertise of so many other disciplines, because he was just an ordinary carpenter, as he called himself, a surgeon who happened to focus on the brain, trying to understand it. And understand it, he needed so many people around him, and that's one of the things that he described. Alan Gregg, who was one of the early founders, early executive directors of the Rockefeller Foundation, in his autobiography said, the most important investments the Rockefeller Foundation has made, and they are many, have been investment in people as opposed to things or concepts. And the single most important investment we've ever made was in this young man, Penfield, who was doing this integrative work in Montreal in the 20s. And so this notion of integration, innovation and entrepreneurialism coming from integration of knowledge, I think is so crucial to us in the century. Yesterday, I spent the entire day, my attention span, it's unusual for me to spend an entire day on any one thing, but I serve on the board of the Smart Systems for Health Agency for Ontario, which has been spun out of the Ministry of Health with a responsibility of investing about $150 million a year in the networking, the digital communication of our health systems and health professionals in the early days. And as we spent that one day together, I was struck again and again and again of the important need we have for highly skilled people, and especially people that combine those innovative, entrepreneurial, coordinating qualities of bringing different disciplines together, particularly as they present themselves in somewhat different clothing today. I can't think of a better person to be symbolizing that and describing that kind of exciting integration than Tom Chau today. And Tom, we're so glad to have you back here, because what we're attempting to do is to create a platform of teaching research programs in this university in the broad health informatics area that does exactly that, that is adaptive and integrative and innovative and brings together disciplines in a very synergistic and very rich manner. So welcome home. Thank you.
Thank you. Thank you, President Johnson, for those kind words. And I want to start off by thanking my hosts today, Shirley Fenton, Professor Covey, and Professor Don McCowan, for their kind hospitality. It's great to be back here, and it's even greater to see the growth at the University of Waterloo in this area of health informatics and in the area of evidence-based healthcare, which is so important to all of Canadians. What I wanted to do today was take the opportunity to tell you about some of the work that we're doing at Bloorview MacMillan Children's Centre in Toronto, and describe to you some of the ways that we're using technology to enable children with disabilities to achieve their personal best. Now, I'm going to work backwards and explain this agenda, but before I do that, I want to tell you about the new model of disablement, or new way of thinking of disablement, which is a shift from the conventional thinking of people with disabilities and how they exist in our society. Before doing that, I want to start off with telling you about the magnitude of disability in our world as a reality. This graph here shows across different age segments in Canada the prevalence of disability. And as you can see, there's a steadily increasing trend as the population segment ages. And by the time you reach about 65, you're looking at about 1 in 3 people having a disability. And by the time you're 75, it's 1 in 2 people. And even in the mid-range, it's not a insignificant number. So disability is actually a more prevalent phenomenon than we would think at first thought. And what this translates to in terms of sheer numbers in Canada, this is a 2001 estimate from Statistics Canada, about 3.6 million people, representing about 12% of the population, about 1 in 8 people, are living with some form of disability. Now, in the United States, that number is even more dramatic. It's about 20%, so 1 in 5 individuals are living with disability. Globally, we're looking at about 600 million people. So this is a huge, huge number. And this is even a conservative estimate, because a lot of the developing countries where the incidence of disability is very high, they don't have the proper mechanisms to report these numbers. So the real number, I think, is somewhere between 10 and 20%, and perhaps closer to 20%. In terms of the activities in rehabilitation injuring, activities directed at addressing disabilities, you look at the funding in the major sponsors in the United States, and we're looking at about $150 million just invested to build devices and equipment for people with disabilities. So it's a huge, huge area of research. And these numbers are about 5 years old, so they've grown tremendously since then. In the USA, as in Canada, the population is aging, as many of you know, and it's estimated by the year 2030, that segment of the population will have doubled. So again, recognize it's going to be a significant factor. The MIT Age Lab estimates that about $29 billion a year is lost to industries and businesses because people have to take time off work to care for elderly parents. So a huge economic impact and implications. The assistive technology industry alone is almost $3 billion in the United States. So again, nothing small that is not small and cannot be ignored. So now that I've told you about the magnitude of disability, and I hope you can appreciate that it's something that's prevalent and it's everywhere, and at some point in our life, maybe this is something that we're going to live with. I want to tell you about the thinking towards disability. And this is what has been termed the biopsychosocial model of disability, stemming from the World Health Organization's 2001 release of this new classification system. Now, this new classification system is intended to provide a common language for communicating across disciplines, across countries, across cultures about disability and functioning. And one of the main contributions is this systematic coding scheme for health information systems. Now, there's a number of fundamental tenets of the ICF, and I'm going to talk very briefly about the ones highlighted in red and show you how this is different from our conventional thinking of disability. Now, in the ICF, there's 3 domains of health, and they are body functions and structures. So that addresses biology and physiology of your body and how that relates to your health. Their second domain is what's called activities. So those are basically all your tasks of everyday living. And the third domain is participation. So the social settings, social milieus in which you perform your activities. And to associate with each of these domains are 3 terms that describe a loss of function in those domains. So impairments, you can have impairments in body functions and structures. You can have limitations in activities and restrictions in participation. So you notice the words like handicap are no longer used in this classification system. Another important principle of the ICF is that now it's a universal model of disability rather than a minority model. And what I mean by that is that in the universal model, we recognize that everyone may have a disability. So it's just not a segment of the population. It's not a certain label or category of individuals who live with disabilities. It can be anybody. So, and it's a continuum of severities. And disability itself is multidimensional. In terms of universality of potential disabilities, I include this quote here by George Washington Carver, who was the first African-American faculty member in Iowa State University. And he says that how far you go in life depends on you being tender with the young, compassionate with the aged, sympathetic with the striving, and tolerant of the weak and the strong. Because someday in life you will have been all of these. So this is the whole universal notion that someday in our life we will be the ones that are weak, the ones that are vulnerable and need to be cared for. Dr. Gregor Wolbring, and again I include this quote to emphasize this notion of that we're moving away from this minority kind of model. He is a faculty member at the University of Calgary, and he is born with no legs due to the thalidomide drug. And he says that he refuses to see himself in the defective framework. He says, I don't accept the defect label because I have no legs. I see myself as a person with a non-mainstream body function. And Dr. Gregor Wolbring is quite a remarkable individual. He doesn't use a wheelchair on campus. He crawls around on campus. So if you can imagine that, seeing a faculty member crawling around. And this was actually an article about him in the recent Abilities magazine, and it shows him crawling upstairs on campus. So here he's challenging the whole notion of these minority and labels. Another very important principle of the new classification system is the idea of medical versus social model. In the conventional thinking, disability was always framed within this medical model. So when someone had a disability, it was always a personal attribute. So there was something wrong with the individual. And so that implied that when we did interventions, we had to fix the individual. Diametrically opposed to that kind of thinking is the social model. And in a social model, we don't view disability as a personal attribute. We view it as an attribute of the environment. So a person's only disabled, or a person's only has a disability because of the environment. And so in terms of intervention, we should be changing the environment. Now, these two are extreme viewpoints, and neither one is sufficient on its own. So as I mentioned, the 3 domains of health now. So this is the new kind of model of disablement now. These 3 domains are understood to define your health condition. And very important, overarchingly important to these 3 domains is this idea of context. So when we look at body functions and structures, activities and limitations, we need to look at the context in which the person exists. So these contexts can be broken down into personal factors and environmental factors. And when we say that someone has a disability then, the understanding is that it's something that's related to activities or participation. So limitations of activities or participation. So these are just examples of environmental factors. Your built environment, your physical environment, the building within which you work or function, the climate, the weather, the road surface, things like that. Personal factors, well, actually there's an important point here in terms of environmental factors. The idea is that if someone has a body function impairment, that doesn't necessarily lead to a disability. So here's an example of someone in a wheelchair, and they're confronted with the staircase. Now, in this situation, this person's inability to move their lower limbs becomes a disability, strictly because of the environment. If we equip this building with with ramps and elevators, that disability is removed. So his impairment is no longer a disability. Personal factors include things like cultural background, gender, age, social background, coping style, etc. So basically all the personal history, personal information related to the individual. Now, the whole new ICF model, because it places emphasis on the social aspect of disability, I just wanted to present a few slides to hammer home that point. This is a quote from a 17-year-old girl who's living with the effects of spinal cord injury. And she says that the most important battle that she faces as a person with spinal cord injury is the battle to belong. It's not the battle to be mobile. It's not the battle to get an education. It's the battle to belong. And she says, by belong, I mean to feel that I am part of my community, my school, to have a feeling of being welcome. So it's a constant struggle for people with disabilities to fit in socially and to be socially integrated. And that's an aspect that we're now recognizing with this new model of disablement. This is an ad from Easter Seals campaign, which they had launched some years ago to raise awareness about disability. And it says that sometimes people meet the disability before they meet the person, and how true that is. This is a slide that I like to use. Look at these individuals, and they have a variety of different facial deformities and facial disfigurements. Now, these individuals do not have any other body functions or impairments, so they're able to move their limbs, they're cognitively alert, they're cognitively aware just like any of us, but they have a disability, and that disability is completely socially created. They have no functional limitations, but they still have a disability. They're not able to get through school, they're not able to compete economically in terms of getting a job, and they're not able to maintain a circle of friends. Why? Simply, it's completely socially created. So that's the whole biopsychosocial model of disability. And I think that has certain important implications for those of us that are trying to develop solutions to help people with disability. So before I describe what this means in terms of embracing the model, I just want to present a definition of rehabilitation engineering so that we're all on the same page. And this is a definition from James Reswick, who's one of the North American founders of rehabilitation engineering practice and research. It's simply, he says, is the application of science and technology to improving the quality of life for persons with disabilities. So it's a very broad definition. And assistive technology, I just took this from the United States Assistive Technology Act. This is basically the accepted definition of assistive technology. So essentially, it's any kind of hardware or software whose intent is to maintain or increase function for someone with disability. So what does this biopsychosocial model mean for those of us who are working with technology to help people with disabilities? This picture is taken from the World Health Organization's photo contest. Each year they hold a photo contest for pictures, black and white and color pictures of disability. And this picture is a little boy pushing maybe perhaps his older brother on an asphalt road. Now, what this biopsychosocial model of disability means is that when we are addressing, when we're trying to come up with a solution for an individual, we obviously need to look at the individual's needs, the individual's impairments, and that we've done all along. We need to consider the technology, and in this case it's a manual wheelchair. But in considering that technology solution, we need to also consider the context within which the individual functions. So in this case, is this wheelchair going to be pushed over an asphalt road? Is it going to be pushed over a cobblestone road? Is it going to be used indoors, outdoors? The whole context is going to be used at school, in the schoolyard. Where is this wheelchair going to be used? How is it going to be used? And the other important factor that we've always overlooked in rehabilitation engineering is the role of the caregiver. So who is actually going to be the person pushing this wheelchair? Is it going to be the little brother? And if this is the case, those handlebars are too high. Right? So these are things that we never looked at before. And this biopsychosocial model of disability is challenging us now to take into account all those all those context factors into devising solutions for people and their families with disabilities. So now I'm going to describe very quickly the way in which we are trying to embrace this biopsychosocial model through intelligent systems. And I like to argue that the approach of intelligent systems fits actually very nicely with this new model of disablement and function. In this context, we can think of an intelligent system as one that organizes different pieces of information. And if you look at all these different colored shapes, think of them as different pieces of information about the child, about the activities that the child does, or about the context in which the child does these activities. I talk about child because I'm from a pediatric institution, but it could be any individual, really. And what the intelligent system does is it self-organizes this information about the child context and activities. And in particular, a dynamic intelligent system is one which does this organization, but over time. So it evolves itself as the person's needs, preferences, abilities, environment, activities change over time. And that's what I'm trying to show, these little shapes moving around as the time scale moves. And this is probably the only equation I'm going to put up. It's just in terms of captivating all of this, it's really one approach is just to allow a bunch of free parameters to be self-adjusted as we try to map the inputs. So these could be physiological signals or indicate user intentions and time into some desired output. So 4 themes I'm going to present now in terms of that I think intelligent systems help to reflect or do reflect in the biopsychosocial model. The first one is that with intelligent systems, we have the opportunity now to transfer the onus of learning, the human-machine interface, from the child to the machine, or from the individual with disability to the machine. So the focus is on human functioning, which is part of that model of disablement. In traditional assistive technologies, the user has to go through a huge learning curve, and it's a considerable amount of training to learn how to use a device. But with intelligent systems now, we can actually teach the machine to adapt and to customize itself to the idiosyncrasies of the user. A second theme, which is echoed in the WHO ICF, is that the individual is okay. So we no longer need to fix the individual. Because we have this intelligent systems, we can actually now have the systems change the environment or change itself to suit the user. And again, so this implies that we're departing from this minority model of disablement. The other important theme is that now with intelligent systems, technologies can be context aware, and we can now bring take into account things like personal factors and environmental factors. In terms of a context aware system, it might look something like this, where we have an intelligent system where we feed it personal factors, so these are information about the individuals and friends and the family, perhaps the patient's medical record. And then we have sensors that go out to the environment and feed information to this intelligent system, which is assimilating all this information and in turn sending some kind of feedback through some interface to the user. So the fourth theme that I think is echoed in the intelligent system is a recognition that disability is dynamic. So like many things in life, disability is not a static entity. Even for people with chronic or long-term disabilities, sometimes the conditions may progress, the environment may change, or a person may grow. As in the children, there's developmental change. So these four themes, I think, are kind of reflected in all the work that we do in terms of rehabilitation engineering, from building devices, coming up with novel assessments and innovative interventions. And they kind of help to ensure that the solutions we come up with are developmental, in other words, that they're changing or adapt or keep up with the child's growth. They're ecologically relevant, so they're relevant to the context, and they address not just the body, but activity and participation. So now I'm going to get to the exciting part of the talk, which is the examples from pediatric rehabilitation from Bloorview, MacMillan. So I don't know if I'll have time to get through all of these, but we'll play it by ear. The first one is a non-contact communication aid. So here we're trying to fulfill the needs of individuals with very severe motor disabilities that are unable to communicate for whatever reason. And in particular, we're looking at children in critical care and palliative care at the Hospital for Sick Children who have suddenly lost their ability to speak. So one day they're able to speak, the next day they've lost that ability. So some of these kids have brain tumors that are removed, and as a result of the surgery, they're unable to speak for 6 weeks up to 6 months. Some of these kids are dying from incurable brain tumors, and in that palliative process, they actually lose their ability to speak. Some of the kids are in critical care, and because they're in critical care, there's multiple intravenous lines, there's physical restraints, there's a high level of fatigue that compromises their ability to communicate. So a couple of approaches we're taking to this communication challenge. One is a brain-computer interface, which I understand there's people here at Waterloo that are also working on this. And this is what it might look like. Typically, a child would wear a cap that's embedded with a number of electrodes, and it would feed into a computer that analyzes the signals from the person's thoughts or EEG signals, electroencephalograms, and we would generate either commands for control or communication. There's a well-known potential in EEG literature, the Barite shaft potential, which precedes motor activity, which is easily detectable. And here I just show you some very preliminary results from some of our recordings from my graduate students. And this is EEGs from 4 different recording sites over the motor cortex. And this is when the individual was thinking no. So if you pay close attention, when I flip the slide to yes, you'll see there's quite a qualitative difference. See, that's yes, and this is no. So we're in the process of quantifying what that difference is. But this shows promise that potentially we could use this to help people express their preference. The other way that we're looking at this communication challenge is through development of a gestural interface. So we have developed algorithms, and this is a child in critical care. So you can see he's ventilated, and his arms are restrained. You don't see that, but he has no way to communicate except through his eyes, through movement of his eyes. So we have developed algorithms to isolate the individual's face in cluttered, unconstrained environments. And upon isolation of the face, we can track the activity of the eyes and allow them communication of some very basic needs. Now keep in mind here, we're not trying to provide the individuals with full-fledged core vocabulary, extended vocabulary. We're just providing them the opportunity to communicate the very basic needs, like things like pain, hunger, medical needs needing to be suctioned, fear. Sometimes the kids will ask someone just to hold their hand. In terms of gestures, if we're not only emit facial gestures, we have developed algorithms that are independent of the body site. So you can use your head, you can use your hand or fingers, or any body part to communicate. So whatever function, voluntary function you still have, you can use that to communicate. An example might be if you move your finger in different positions, you can elicit these different utterances. I'll just skip through that one. So what we're looking at then in terms of non-contact communication is the harnessing of gestures and thoughts and processing them through an intelligence system to allow people to communicate. Unfortunately, I can't show you a real clip of this yet. Another project that we're working on is the development of an aspirometer. So that's not a real word, it's a word we coined to detect aspiration. So aspiration is when someone inhales their food. And this is a prevalent phenomenon in children with neurological pathology, but also quite prevalent in the geriatric population. If you go into a nursing home, about 50 to 60% of the residents there will have swallowing difficulties. So this is a sagittal view of this yellow is perhaps some kind of food or liquid that's going down into the esophagus, and it's a complete epiglottic closure. And what happens in the aspiration situation is some of the food or liquid goes down into the windpipe and into the individual's lungs because of their neurological impairment. So they don't have the protective mechanisms, say, to cough and gag and bring the food back up. So what happens is that their lungs get consolidated, they get chest infections, and all of this is irreversible. And in the worst case, it can lead to death. So what we did was we attached a sensor just below the thyroid notch to a child, and we collected the vibration signature that was produced when the child was feeding. Now, why we did this was because a number of clinicians told us that we think we can hear differences, they said. They felt that with a stethoscope and sitting there while the child was feeding, they could hear differences between swallowing and aspirations. So the gold standard for detecting aspiration is a procedure called videofluoroscopy, which is a very unpleasant procedure for a child. Essentially, we put them in an X-ray, and we feed them food that's called ovarium, so that it shows up on the X-ray. And this is what the video might look like. This is an actual videofluoroscopy video. It's from the side view again, and it's kind of small here, but you see the black substance going down. That's actually the swallow, the food going, the bolus going down. So we can actually see exactly where the food is going. So obviously this is a procedure you can't do all the time. And so we wanted to come up with a way where we could detect aspiration non-invasively and outside of the institutional setting. So what we have devised is a very simple system that flashes a green light when a swallow is detected, and it flashes a red light when an aspiration is detected, based on this vibration signature that we were recording. And we have just recently patented this device, and we're hoping to bring it to the market within the next 2 years. Just in terms of the predictive value of this diagnostic test, it's quite high, and in fact it's better than the best trained clinician. So we think it has significant clinical potential. And I think this is a clip of just one of the children wearing the actual device. You can see he's actually got the device around his neck just on a Velcro band. Don't have volume here, but his mother is basically describing the feeding situations, and that they're afraid to leave the child with a grandparent or an aunt or an uncle because they're not able to tell when the child is aspirating. And so they always have the fear. And this device will give them that peace of mind when they're feeding the child. So if they do see the red light going on, they can slow down the presentation of the food, or thicken the food, change the consistency, or change the positioning of the child. And we envision that this device would be something that parents could carry around in their purse, and they could attach it when the child's feeding in whatever scenario. And eventually it could be wireless. We also now have the capability to log an individual's swallowing activity over several months. So we can, after an assessment in the hospital, we can give this device to the child, and we can record all their swallowing activity for the next 6 months. And then we can come back at the follow-up assessment and see how they've been doing in terms of swallows and aspirations. This one is a bit of a cute one here in terms of the videos I'm going to show. The augmented environments are intended to enhance function for individuals by modulating their existing environment, their real physical environment. So if you think of your real physical environment, and if I move my hand over here, nothing happens because this is just space. In an augmented environment, we augment the physical environment by giving additional properties to this space. And those additional properties can be information or cues to the individual, or other auditory or visual stimuli. And the one that I want to talk to you about is the virtual music instrument, which we have developed at Bloorview MacMillan. that allows children with severe physical disabilities to play music. And essentially, all they have to do is move through space, and they can generate music. And we actually have a service program, outpatient service program now that's been running for almost a year and a half, where children come in for music lessons, like taking piano or guitar, to practice a song and go home and practice on their home computer, which also has the same system. So I'll show you a quick clip of this. Oh, I need the sound here. It's not the same without the sound. Just give me a second. Turn on the sound here.
Love it. They start off playing things like Twinkle Twinkle Little Star and are so
You able to hear that?
that they're able to produce these sounds and a song that they recognize, and talk about how when they go to school and their friends can play violin, how I can play violin too. So if we want to go from the beginning, we go green, orange, yellow, orange, yellow, red. And they just feel so confident and know that they can participate in the same way as their peers.
So I have one more to show you. This is
Say now, Edward will play Twinkle Twinkle Little Star.
So you see, it's a real thing. He made mistakes, right? It wasn't pre-recorded. Yeah. So that's the augmented environment. We're working on a number of different augmented environments as well, but that one I thought was cute to show. We're also working on, I guess, the traditional area of rehabilitation engineering when you think of it in terms of prosthetics. But we're taking a whole new approach in that we're harnessing a new type of signal called mechanomyography rather than the conventional electromyography, which many of you may be familiar with. Essentially, when you voluntarily contract a muscle, it generates a vibration. And this vibration is detectable at the skin surface. So traditionally, we've always looked at the electricity that we could measure from polarization and depolarization of the muscle membranes. Here we're looking at actual physical vibration. And if you take a cross-sectional view, that vibration is generated in a manner similar to this. So you think of a muscle as a bead on the string, and you pull both ends of the string, and then the bead will vibrate. A favorable property of this mechanomyography signal is that it propagates through soft tissue. So if the individual is flexing, say, their biceps, that signal will traverse down their limb, longitudinal to the excitation site. And this is important because now it means that I don't have to measure muscle contractions over the muscle bulk. I can measure them distally. And this allows us then to much more flexibility in terms of designing prostheses. We can remove all the wires and all the electronic components away from the muscle area and actually put them in a distal location. One of the biggest challenges with measuring mechanomyography is that it's a very low frequency and it's a very weak signal that's very easily contaminated. So essentially it's a vibration that we transduce into sound, but it's very easily contaminated. And because of this, it's never been used practically for prosthesis control. We have developed a sensor that is able to overcome this problem. And essentially what we do is we have two transducers placed back to back, a microphone that measures useful muscle vibration, and an accelerometer that's simply dedicated to measure external noise. And then we have some smart algorithms to tease those pieces of information apart. In one very simple scheme, is simply to use the accelerometer signal as a gate. So you see the little hand here that will open and close the gate. So when we see a signal from the microphone and nothing from the accelerometer, in the simplest scheme, we can just let that signal pass to the prosthetic controller, and then an individual can do something useful with their prosthesis. When we see a signal both at the accelerometer and the microphone, remember that the accelerometer is dedicated to measure noise. That means there's actually noise being generated. So what actually happens when the accelerometer signal appears is that that gate opens and does not allow the microphone signal to propagate to the controller, so there's nothing happens. So this is just a very simple control scheme. Now this is actually a picture of what we call a soft socket. Now if any of you know about prosthesis, all the existing prostheses are hard. Right? So there's a hard socket that goes over the individual's residual limb. And if you're talking about a below elbow amputee, the hard socket needs to lock over the individual's elbows. So even if you're able to rotate your forearm, you still have this natural rotation. You're not able to do it once you wear your prosthesis. And all the weight is suspended over your elbow condyles. With this soft socket, it rolls on like a sock over your residual limb. Extremely comfortable, and it doesn't have to lock over your elbow, so you still have that rotation function. These little squares at the front here are actually the sensors, and these sensors are embedded right into the silicon socket. So there's no more issues of sensor placement. We roll them on and the sensors are in place. Because the sound is propagating, it doesn't matter where we're measuring them from. Here's a clip of a little girl who's actually using one of our prostheses here. I can cut the volume here. So this prosthesis you're seeing is being rolled on to the little child's residual limb. And she's actually using this prosthesis for the first time during this recording, and she's never been trained on it. And using an array of 3 mechanomyography sensors, she's able to control this prosthetic hand that's freestanding here. Now, there's nothing impressive about the hand. This is the same hand that's been around for 30 years. But it's actually the control system that's innovative in this setting. And this mechanomyography control system, we believe, will be able to provide, has the potential to provide individuals with multifunctional control, say control of different grasps and different functional movements of the hand. And why we say that is because with the muscle sounds, or mechanomyography, we're getting, for the first time, activity from deep muscles. With electromyography, we only measure the superficial muscles. We have no way to tap into the deep muscles. And we know the deep muscles are being activated as well. But because sound propagates, we're getting all that deep muscle activity. And so what we're working on right now with a number of graduate students that are trying to develop ways to harness those deep muscle signals in conjunction with the superficial muscles and translate those into motor programs for multi-articulate control. Okay, so I think I have time to tell you about this last one here. Another area that we're looking into is very important, I think, and a very innovative area of rehabilitation, and this is the concerning temporal fractals. So many of you may have heard of fractals, and you've probably seen pictures of nice, colorful pictures of spatial fractals that have been generated. And essentially, a fractal is just simply an object that's self-similar. That's what a spatial fractal is. So that means if you look at it at different scales, it looks like itself. Right? It's self-resemblance. Temporal fractals means that if we look at a time series, and this could be a physiological process, over different time scales, so say this red window, we slide it across and compute the fluctuations, we get a dot here on this graph. And then we widen the window and we compute the fluctuations again, and we keep repeating this process at different time scales. We get a power law relationship between fluctuations and scale. Now this is important because it indicates that this physiological process has something called long-term memory or self-similarity. And this is particularly important in gait, which we're studying. So this actually time series here could be a stride. This actually is a stride interval time series. So it's actually the time between successive steps when a person is walking. And for many years we thought this was random. We thought that the steps you took now and 10 minutes from now and 20 minutes from now are unrelated. But what this is telling us is that the brain is actually planning ahead based on historical information. And in fact, it's planning so far ahead that the dependence is up to the range of thousands of steps. So steps you take out here and steps as you walk around Ring Road are going to be all related. So your brain is assimilating all that information. Now, the interesting thing about these fractal measures is that they're extremely easy to these fractal phenomenon is that they're extremely easy to measure. We can place sensors anywhere when a person is walking. So, for example, we could put a switch in the shoe. We could put an electrogoniometer at the knee. We could put an accelerometer at the level of the sacrum to measure the vertical acceleration of walking. As long as we compute the time between events, we're able to tap into these fractal patterns. Because these fractal patterns require that we measure over long periods of time, we need to do these measurements outside of the institution. So a lot of these studies are done outside, around, on an indoor track, on an outdoor track, or around a long length of the hallway. Now, most of you, or actually all of you, probably have a scaling exponent close to 1, which is the neurologically healthy level of scaling exponent. And what does this mean? It means that the steps you take now are related to the steps you take 10 minutes from now, and those to 20 minutes from now, and that relationship diminishes over time. And these kind of relationships are very robust. So it doesn't matter what speed you walk at, a self-selected speed, a fast speed, slow speed, those dynamics are going to be there. And they're going to persist for up to 1 hour of walking. Now, interestingly, you can obliterate your own dynamics if you walk to the beat of a metronome. So if someone plays a steady beat, completely periodic beat, you're going to lose your dynamics. Or if you walk on a treadmill, you also lose your dynamics. So as you can begin to sense, this has incredible implications in terms of rehabilitation, because we actually have people walking on treadmills as part of the rehabilitation. And what this theory is telling us is that perhaps that's not the best way to restore function, because that's not the way the brain regulates motor activity. Now, we don't understand fully why these fractal mechanisms exist, and there's a number of hypotheses that have been thrown out. One is that these fractal mechanisms exist so that our energy expenditure while we're walking is optimized, or that we provide it with optimal stability and balance, and that we can respond to perturbations. One of the most interesting hypotheses is what's called a hierarchical synthesis hypothesis. And this hypothesis basically says that when we're walking or performing locomotor activity, we're receiving inputs from the environment at all different frequencies. So for example, we're receiving visual stimuli at a fairly high frequency. We're receiving auditory stimuli at a different frequency. We're receiving proprioceptive input from our lower limbs. We're receiving vestibular input to help us balance. So all this information is coming into our brains, and they're all coming at different frequencies. So perhaps it makes sense that when we regulate locomotor activity, the brain also generates control signals that come out at different frequencies. And it's the combination of these different frequencies that generates the fractal patterns. The important implication in rehabilitation in terms of these fractal patterns is that in the face of pathology, we lose these fractal patterns. So these are different populations that have been studied. Huntington's, ALS, Parkinson's disease, and this is just due to natural aging, and cerebral palsy, which we have done at Bloorview, MacMillan. So in all these different pathological populations, these fractal patterns are diminished to varying degrees. And in fact, the person's walk becomes more periodic, it becomes more regular. And this is kind of counterintuitive, because you would think that if a person is walking at a very regular pace, this would actually be a good thing. But in fact, this is actually a sign of pathology. And so some of these are some of the implications of, perhaps potential implications of diminished dynamics. We don't really know at this point in time. But what we do know is that periodicity is bad. And in fact, this does not only applies to gait, it applies to heart rate. When your heart rate becomes completely periodic, you're going to have an adverse event. You know, it could be the onset of congestive heart failure. As well as we also know for ventilation, if your ventilation becomes completely periodic, you're in trouble. So all these different physiological processes we're beginning to discover are regulated in a fractal manner, and they're not strictly periodic. So quite a significant challenge to our conventional thinking in terms of rehabilitation. In the conventional thinking, we always think that the information is contained in absolute value. So a certain joint angle is what we're trying to achieve, or a certain range of motion. But what this fractal viewpoint is telling us is that the information is not in the absolute values, but actually in the fluctuations. And the other important, there's a number of important implications. The other important implications is that the periodicity is actually bad. And I have to emphasize this because I think this is a significant implication for people with neurological impairments. And the other, another important implication is that we're looking at a system-wide measure when we're looking at fractal patterns rather than a localized, very isolated viewpoint. So what are the implications of the existence of these fractal patterns in rehabilitation? Well, as I mentioned already, then perhaps repetitive periodic treadmill training is not good. Walking while listening to computer-generated music is probably also not good for your neurological health, because that is completely periodic. And we know that listening to a metronome, you override your dynamics. The other important thing, and also echoes this biopsychosocial model of disability, is that we need to consider the context of walking. And I'll come back to that point in just one moment. The idea of potentially restoring someone's fractal dynamics, we've been toying with this idea that maybe we can rig up a treadmill that is going to generate a fractal velocity pattern. So it doesn't, the treadmill does not go at a single speed, but keeps changing its speed in a fractal manner. Then maybe we can affect a person's timing so that it also evolves in a fractal manner. And potentially, maybe we can entrain their dynamics. So basically, can we reprogram the software and leave the hardware intact? All of our interventions today for people with neurological pathologies address the very peripheral problem. It does not address the central problem. So we do surgeries on the lower limbs, we rotate bones, we sever muscles and reconnect them elsewhere. We do electrical stimulation of muscles. So all the interventions to date are addressing the peripheral problem, but not the central problem. And the point about walking in context, we know that children and perhaps adults as well seldom walk alone. So we often walk with other people. There's often other sensory stimuli that we receive while we're walking. There's noises from, the traffic and overhead and airplanes and birds and things like that. And there's other cognitive processes that are engaged. So we often talk to people when we walk. So we've never looked at that in terms of rehabilitation engineering. So I think this bears incredible potential in uncovering new information and potentially new interventions. So there's a number of other projects that we're engaged in the lab that I'm not going to talk about today. But these are, again, different ways that we're using technology to enable children with special needs to achieve the personal best. One I just wanted to mention very briefly is the self-selected expressions of functional intent. In the conventional way of rehabilitation, we always see what function the child has, and then we decide how that function is going to map to a useful activity. And this last approach, this last project here, is kind of flipping the tables, and we're saying to the individual, show me what function you have, and then we're going to let the machine, we don't tell the individual to do specific things. We tell them to demonstrate their function, and then we have the machine discover what it can recognize. And then the individual can decide how that function gets mapped to useful activities. So this is basically what we have talked about. I hope I've enlightened you a little bit in terms of thinking of disability, which I think is the major shift and major change in the whole arena of disability, in that we're no longer considering disability to be a personal affliction, but something that's much more complicated, multiple dimensions, and very much a function of the environment and social attitudes as much as the person's own physiology and biology. And I think that kind of thinking has huge implications on how we deliver service and conduct research in this area. So I think I'll leave it at that and hand it over to Shirley.
Dominic, will you lead our discussion, please?
Sure, it was a really interesting presentation, and what I'd like to do is open for questions and comments from people who are here. In order to get this so the non-studio audience could hear it, I'll pass, or Shirley will pass, a microphone. If you just give us a second to get to you, we'll bring the microphone to you. So questions or comments?
One question. You talked about commercializing that Aspirometer, or I've forgotten exactly the name of it, but I know what you're talking about. And that seems to have wide applicability. And so it makes sense to commercialize it, make it available to a wide audience. Many of what things you're doing, I suspect, are very limited in the audience that they're addressing. How are you going to make those more widely available?
Mm-hmm. So I'll give you an example in terms of the muscle sensor. The mechanomyography sensor is another one that we're thinking of commercializing as well. And obviously that has a very limited applicability based on what I presented here, mainly people with upper limb amputations. Right? So another useful feature of that mechanomyography signal is that when a person fatigues, or when the muscle fatigues, that properties of that signal change significantly. So there's a shift in terms of the frequency content of the signal, and the amplitude of the signal changes significantly. And we can detect that very easily and very definitively. So we are thinking, and this is just an idea, that potentially that muscle sensor device could also be applied for exercise physiology or sports medicine, where, for example, if a person is walking on a treadmill, they can just stick on these sensors and they can tell them when they're starting to fatigue or when they're pushing themselves to the limit, so to speak. It might be also something that people that are lifting heavy objects might use, so like to monitor the muscles of the back, and so they know when they've reached their limit or when muscles are fatiguing and they're going to be at high risk of injury. So we're thinking of other applications outside of the narrow field and narrow applications that we're trying to address.
Way back in my past, we set up a biophysiological laboratory at the University of Western Ontario. And what was interesting about your fixed rate or synchronous kind of thing was that we found that very depressed people, actually their heart rate converged on a fixed rate. And it was an indication of a problem. And as you pointed out, that the variability in heart rate prevents the heart from locking into or creating bad rhythms. What are some of the other things you're finding out in that area? That's kind of interesting. I understand that the people involved in complexity theory have been working hard on that. Can you talk about that anymore?
In terms of other phenomena?
Yeah, the phenomenon.
Yeah. We have found actually this past summer, and we're just writing up this paper, that in repetitive graphomotor activity, so if you're writing repeated letters over a long period of time, and you say peg an event, say like the top of the O or top of the T or whatever, there's actually a fractal pattern there while you're writing, you're doing handwriting. And we also did the test where we actually asked the individual to time their writing to the beat of a metronome. And again, the dynamics were diminished. So even the fine motor activity, something that we take for granted in handwriting, also exhibits these dynamics. People have also showed in tennis strokes, I guess if you're a good tennis player maybe, the repeated tennis strokes are also fractal. Eye blinks are also fractal. So there's a wide range of physiological activities. So these are all temporal fractals I've told you about, but spatially inside the body, physiologically, the branching of the bronchioles in the lungs is also fractal. And the hypothesis there is that you can maximize the surface area using a fractal branching mechanism. The arterial exchange, the capillary exchange of venous and arterial blood is also fractal, spatial fractal. So it's just prevalent in nature. And somehow through the evolutionary process, this has come out to be the optimal way for things to be organized.
When you force the handwriting through your rhythm introduction into a non-fractal pattern, a relatively rigid rate, was there a change then in the handwriting or in the effort associated with the handwriting? What was the effect of that?
In terms of the handwriting itself, we didn't really look at the qualitative aspects of the handwriting. I mean, qualitatively it appeared the same. We really couldn't see a difference in terms of the handwriting. But it may be but these were all neurologically healthy individuals, right? So they were able to restore their dynamics afterwards. We're also looking at this in kids that actually have fine motor difficulties. And so maybe in those children, the dynamics are perturbed in a way that is going to be very different.
We have a number of people here. I know that Applied Health Sciences is quite a large gait analysis group. I don't know if anyone from that group is here or has any comments on this. Do you want to comment?
Sure. I mean, it's always very interesting about the whole idea of variability. I mean, certainly when people will look at people that are standing in place and trying not to fall over or obtain an equilibrium, and you're always challenged on looking at the variability of how they stand. That, some people are just more variable might be better, and they often get caught in trying to look at somebody with a steady, consistent pattern as being good. But we're also challenged with, the multi-dimension variables of looking at somebody walking and the changes that can happen at one joint versus another joint, and it's just the real flexibility that we have of selecting different muscles, different joints to do things. That is the richness. Mm-hmm. Yet, often when we look at analysis, we're looking for differences in consistency.
If I would just comment very briefly, this whole kind of redundant kind of mechanism in the locomotor system is actually part of this fractal behavior, because we have, as you suggest, many modes to choose from. And interestingly, when we look at children, they actually have less modes than adults. So their fractal number is actually different from adults. And as they mature, they start to learn all these different modes. And so young children that are just starting to walk, they're less stable, they're prone to falls, right? Because they don't have as many modes to choose from. And in fact, in the elderly, they revert back to that situation where they lose these modes now. And so then again, they're more prone to falls and fractures and things like that.
Okay, with respect to mechanomyography, does it make the fitting of prostheses easier on, for instance, does it grow with the child? I know when you actually use myoelectrics, you're continually redoing it over and over again to try and get the exact position, and yes. With mechanomyography, you're probably better off.
Well, the socket itself at this point would still have to be remade, right? Because the socket is cast on the child, right, at that instant in time. Excuse me. What we're not so much concerned with anymore is the placement of the electrodes. So in the old scheme of things, not only did we have to redesign the prosthetic arm, we also had to find the sensors, because the musculature is changing as the child is growing. So we have to locate new sites every time. So with the new mechanomyography system, we don't care in terms of the location of recording, because we know that the sound is going to propagate. So I think that would be the chief advantage in terms of the developmental perspective.
Other comments or questions? I guess I'm worried now, so I shouldn't walk with the staying alive beat,
Well,
is that an implication?
Interestingly, if the music is generated by a human being, the implication is that if the human being is the musician, that there would be a fractal pattern there in the music.
That's right. So it has to be a
so you're okay.
Orchestra.
That's right.
So as I do this, so I strut, it's going to be good for me.
So you're safe. So I specifically put computer-generated music, which would be strictly periodic.
I was just wondering if there's variability in fractal patterns, like amongst healthy subjects even. Like, do you get the same fractal pattern from every single person?
No, you don't. There is variability. It's very small variability. Like most healthy individuals would fit in the 0.9 band with maybe plus minus 0.05 standard deviation. It'd be a very small band.
So ideally, is there like an ideal fractal pattern that you should have? Like if you were talking about sort of the whole treadmill idea,
yes,
and involving sort of a fractal pattern in the velocity and changing the velocity in order to retrain the dynamics. Yes. Is there an ideal pattern that you want to train?
Well, for children, we know the numbers are slightly above 1 for the typically developing child. So that would be the goal, is to try to get them back to those numbers. That would be the ideal. So based on studies of control individuals, right?
So you found that there really is sort of less variability in this pattern of variability. Like a pattern of fluctuation is sort of less variable than overall variability in gait, like say stride length.
Well, it's a different different scale altogether, right? Because your gait, for most of us, probably we walk about one's stride per second, probably, or thereabouts, right? And then the variability there can range. I mean, depending on a lot of things, like the surface you're walking on, your speed you're walking on. The important thing is that it doesn't matter how wide that variability is, the dynamics are still going to be the same.
Okay. Thank you.
Others? Not to leave this, oh, got Don.
Have you thought about using this fractal pattern as a diagnostic tool, since you showed a number of different diseases up there?
Absolutely, absolutely. And if that's one of the things that is very much needed in rehabilitation, is objective outcome measures, and this would be an ideal objective outcome measure. So to measure the effect of intervention. So if we give a person surgery, we give them physiotherapy, we give them functional electrical stimulation, do the fractal patterns improve? Apparently this is the ultimate measure of neurological health. So definitely it could be a quantitative outcome measure. And that's really our intention, is to make this available in that sense.
So I was very impressed by your presentation, and among the things I appreciated very much was your taking the conceptual framework of the ICF, the biopsychosocial model, and actually realizing that in terms of your innovation and the technology that you're introducing, and really taking seriously the notion of it's the environment that needs, or context that needs to be adapted, not the individual. Just mention as well, my father-in-law, who's a professional musician, will be, I think, encouraged by your findings of the potential health consequences of computer-generated music. And I wondered in passing if the marketers of Muzak and computer-generated music systems for shopping centers might do better to hire live orchestras to encourage customers to do their Christmas shopping. The notion about the fractal patterns, and I guess generally, my background is more in geriatrics, and I think a lot of what you're doing has tremendous potential for geriatrics. I wonder if you thought about use of any of these concepts, particularly for older persons with dementia, and whether maybe the notion of the fractal pattern might be something to measure, improvements in outcomes for persons with dementia or cognitive impairment.
Definitely. I think the whole notion of measuring these fractal patterns in fine or gross motor activities would definitely apply. So say whether the person's recovering from like a hip injury or what have you, and they're in rehabilitation, you can measure these fractal patterns and see how far they've progressed. And it may be, once we haven't done any stability studies yet, but maybe if we do some stability studies, we can link that up to how stable the individual is, because that's obviously a big issue in the geriatric population, right, and their ability to respond to perturbations. Right? So we haven't made those links yet, but those would be important links to make, and I think they would have a great applicability in the geriatric population. There's also been mentioned, and I don't know if there's any scientific basis about this, in terms of fractal pharmacology, and the idea that drugs should be administered on a fractal schedule rather than on a periodic schedule. So this was something that our Dean of Medicine threw out at me. I don't know if there's any basis behind that, but I think there are applications simply because the body is regulating so many things in a fractal manner, and we know that in natural aging, we start to lose some of that fractal regulation. I think that would be a tremendous indicator of health.
Yeah, wouldn't that be something that, to be some way then to target, sort of individualize the therapeutic regimen, dose and quantity, and that would be, I'm guessing that would have to be individually tailored then, if we decide if it's that kind of a pattern too.
Yes.
Very interesting. Thanks very much.
Thank you.
Really?
Actually, I was just curious about the direction of your brain-computer interfacing research, and I'll footnote that question with, like, for example, you're already using EEG signals that originate from the motor cortex, which can translate well also to movement tasks, such as maneuvering a wheelchair and something like that. So I was just curious about that.
Well, potentially down the road. At this point, we're not that ambitious yet. We just want to be able to establish a communication link so that somebody can express preference. Because believe it or not, that is a fundamental issue for a lot of the kids we see. They're not able to leave the institution because they're not able to express their preference of treatment. And the other challenge that we're looking at, that we're facing in EEG, is that we're looking at the spontaneous EEG. Many of the brain-computer interfaces you read about, they actually do biofeedback training, and a lot of them are evoked potentials. So they either train the individual to modulate their brain waves so that they become very easy to detect, or they present stimuli and measure the response in the EEG. Right? So that makes the problem much more easier to solve. But because we're dealing with kids that are nonverbal, very low functioning, it makes it very difficult for us to do biofeedback training. Right? So we're working with the spontaneous EEG, which is a real mess of information.
Thank you.
But potentially, yes, a wheelchair, any other assistive communication devices.
Okay, thanks.
Thank you.
Others? I don't want to change the topic, but we had the chance to talk to Tom beforehand, and I was quite impressed with the work that that the Institute is doing related to students. I wonder if you could talk a bit about some of the things that are being done with students and how you engage them in these areas.
Sure. At the University of Toronto, we have, at the undergraduate level, a club for undergraduate biomedical engineering, which is a membership of several hundred across the various different disciplines, not all from engineering, from life sciences, physiology, rehabilitation sciences. So very broad representation across campus. And this group is run by students, and so all the executive are student members, and it's essentially funded by various different faculties and departments. And in terms of their activities, they organize talks where they invite speakers to come in on a regular basis. So these are students identifying speakers and inviting them to come in. Most of them are local because of funding issues. But it allows the students to find out and learn more about topics of interest to the students themselves. And they also, once a year, invite faculty members to speak about their respective research areas in order to help students decide what they want to do for graduate school. Now, at the graduate level, we also have a biomedical engineering society, which is more of a social group and consisting of master's and PhD students. And they organize a number of activities that allow students and faculty to intermingle and talk. And as well in biomedical engineering, and also with the help of students, we have annually a biomedical engineering research day, which is a full day of presentations. So we invite a keynote speaker that often comes from abroad. Well, actually, it's always someone from out of Canada. And they give the keynote address, and then we have a variety of student presentations, poster presentations, and we throw in some sustenance in terms of food to entice people further. This Friday, actually, and that's why I've been losing a lot of sleep, is I'm helping to organize the first Rehabilitation Engineering Research Day at the University of Toronto. And similar format, we have a guest speaker who's going to kick off the talk and kick off the day. Then myself and a colleague, Milos Popovich, who does functional electrical stimulation, we are presenting a lecture on the past, present, and future of rehabilitation engineering. And then there's going to be student presentations and posters and the usual food to entice people.
Question in the back? I like that Shirley does all the work.
Just to, I guess, announce that we do have a club for undergraduate bioengineers also at Waterloo. We just started a couple years ago as well.
Good.
Ask me. I'm Bernadette Robin in chemical engineering.
Wonderful.
If not other comments, I just wanted to follow on from Paul's comment, is that after about the December 1st, whenever I hear jingle bells played by live band, dead band, or computer, I immediately get into a rigid anti-holiday rejection mode. So I fully appreciate your talk. I very much enjoyed what you had to say, and Shirley will finalize the session.
All right. Well, thank you very much. I have to say that when I was channel flipping, I told you about that at the beginning of my talk, that I saw Tom on TV, and the thing that really caught my attention was the music program that you developed for kids, and the delight that the children had. It was very evident in the program that they were just thrilled that they could participate in that manner. So I thought, we've just got to get this person here to talk to us about his research, and it's been such an engaging talk. Thank you so much. And a theme that seems to have gone through your talk is time. So this is a little memento from us that might be helpful in that regard. So thank you very much.
Thank you very much.
We really appreciate you coming.
Thank you.
Well, thank you for coming today. I just want to wrap up and say that we will take a break now until January, so we will not have a seminar in December. But on January the 26th, our guest speaker is Dr. William Hirsch. He's an expert in information retrieval and data mining, has implemented a very innovative program in medical informatics at Oregon Health and Science University. So I hope you'll come and see us in January. Have a great Christmas holiday, and we'll see you in the new year.